Hey everyone, the network tournament is coming, so this Monday evening in 306 Soda starting at 7 p.m. and everyone is welcome and encouraged to enter. Nobody is required to enter, but if you have a working project too, we encourage you to give it a try, take a shot, and if you are the lucky winner of the tournament, your group will win gift certificates to Amoeba Records. So if you would like to enter, then one, you're welcome to change your project too and improve it, improve the strategy and the playing beyond where it was when you originally submitted it. And second, the instructions for how to submit your project to the tournament are on the class webpage. You'll need to make some small changes to your network in order to make sure that each student's entry is in a different package. But once you've done that, that also gives you the ability to use the network program to play different students' network players against each other and see how you're doing. Also, I want to mention that next week is Reading, Recitation, and Review week, and we're going to use it to do reading, recitation, and review. So there will be a full complement of lab and discussion section and 2 lectures, and as per university rules, no new material is going to be introduced next week. Rather, we're just going to try to help you prepare for the final exam. And so the lab will be helping you learn to sort faster for the final exam. The discussion sections will be whatever you want help in studying for the final exam. On Monday, we'll have a sorting video, and on Wednesday I'll wrap up. Today's the last lecture of new material, and today what I want to talk about is garbage collection. Objects take up space in memory. If your program creates a lot of objects and then stops using them, and then creates more objects and stops using them, and keeps repeating this loop forever, then eventually you could run out of memory because it's full of junk objects. So Java does the work for you of figuring out which junk objects are no longer in use and reclaiming that memory so it can use it to construct new objects in that same space. So while the Java virtual machine is running your program, it also spends a little bit of time every now and then searching for objects that you're not using anymore so it can reclaim those memory for new objects to use. And you don't have to know anything about garbage collection to be an effective Java programmer, but garbage collection is really interesting because it uses data structures and algorithms, including some of the ones that we've learned this semester. So the Java virtual machine uses a lot of hidden data structures to manage memory. And these data structures, they're completely hidden from your Java program. They're not data structures that you can access, but they're used to manage the heap. They're used so that Java knows where there is free memory in the heap, which memory is being taken up, what objects are taking up that memory. And so it's constantly keeping track of the different bits of memory space that you have, taken ones and free ones, and it keeps them knitted together in what is essentially like an invisible linked list that you can't see, but Java can see. Now, good encapsulation means Java hides that from you, but it's still useful to understand how Java decides which objects are going to be garbage collected. And so that's what we're going to talk about. So what's going on under the hood is Java's prime directive is it must never, ever garbage collect any object that you might actually be able to use. So we have to distinguish which ones you cannot possibly use anymore. And those are the ones that have no reference going to them from another object that you could use. Now, if an object is somehow accessible so that your program might possibly be able to use it again, those objects are said to be live. And the opposite of live is garbage. Garbage is the objects your program can never reference again, no matter what it does. And Java's design makes it possible for the Java virtual machine to determine which of your objects are live and which ones are garbage. And so garbage collection begins at what are called the roots. So the roots are any reference that your program can access directly without going through another object. And the most obvious roots are local variables, but class variables can also be another form of roots. Now, the local variables are all stored in activation records on the stack. And Java's activation records are also data structures, and while the structure of those data structures is hidden from you, Java can look at an activation record and knows which bytes in that activation record represent references. And those references it can follow, and it knows that those objects are live. So those are roots. Also, every class variable by which I mean static variables, variables you've declared static. And these are roots as well, but only if they're reference variables. So primitive variables, they're not roots. Just the variables that actually point at objects are roots. Now, there are two ways that an object can be live. And therefore should not be garbage collected. An object is live if it's referenced by a root. Obviously. But an object is also live if it's referenced by another live object. So for instance, a list might be live because the stack points to it. A list node might be live because the list points to it. Mm-hmm. What about, sorry, what? Okay. So this definition is recursive. I say that an object is live if there's a live object pointing at it. So that means that the second list node in a list is live because the first list node points to it. And the third list node in a list is live because the second list node points to it. And all the way to the end of the list. Another way to say this is to think of all the objects in memory as a graph, a directed graph. And if one object has a reference pointing to a second object, you think of that as a directed edge. And now we're asking which objects are reachable in this graph. So if you run depth-first search on this graph of objects and their references, then you will eventually reach all the live objects by depth-first search. And that's exactly what garbage collection does. It runs depth-first search from the roots. Question over here? Activation record, you know the program stack, the things on the stack that hold your local variables are called activation records. I guess I should have said stack frame. That's right. Did I write this down? All right, a stack frame. I think the textbook calls them activation records, so I wind up mixing up the terms from time to time. All right, so to do depth-first search, one of the things you need is you need every vertex of the graph to have a visited field that tells you whether you've already visited that vertex or not. And sure enough, Java stores objects in memory so that they do have a visited field. It's hidden from you. It's basically a bit in memory that you can't look at with your program, but Java's garbage collector can look at it. And by the way, this is not the only hidden information that objects have that's invisible to your program. For instance, the Java virtual machine, whenever it creates an object, that object has an extra tag in memory that you can't access that tells Java what class that object is in. So Java knows the class of every object in memory. Also, hidden data structures. Your Java program can't probe them directly, but Java can use them. And it needs to use them to do dynamic method lookup. So I want to go into some detail about how garbage collectors work. But before I do that, I need to talk about what memory looks like, what memory addresses are, what pointers are, and what references really are in Java. So this is kind of a sneak peek of CS61C material. So in any modern computer, memory is just one huge array of bytes with addresses. And so your memory actually, on your computer, actually looks like an array. There's a byte, there's a byte, there's a byte, there's a byte. However, most modern computers prefer to read and write 4 bytes at a time rather than just 1, or sometimes 8. And they tend to do it faster if you're reading a byte, if you're reading a word, a 4-byte word, that is aligned. And by aligned, I mean it starts at an address that is a multiple of 4. Also, things like ints and floats, they take 4 bytes each. So your computer will just load them and store them faster if they're aligned on a 4-byte boundary. Each time, so what the Java does for you, what a compiler like Java or C or any other compiler does for you, is it helps manage that space by making certain decisions for you. Like, suppose you want to declare a variable. You don't want to have to think about exactly which byte in memory or which word in memory you're going to store that variable in. You just want someone to pick a space to store that variable, and you don't have to think about it anymore. So that's one of the things the compiler does for you. When you declare a local variable, what that means is that you're naming a memory location. Now, you get to pick the name, but Java picks the address for you. So that's really handy, because that way, if you want to have a variable called Bob, you just name it Bob. You don't have to remember that Bob is at address 74962 in memory. That's Java's job to remember that for you. So now you have your memory looking something like this. As I said, we usually divide memory into 4-byte chunks and store a different piece of information at each 4-byte or even 8-byte chunk. So I'll use memory addresses here that are divisible by 4. And if I declare in my Java program a variable called Bob by writing int Bob, well, an int takes 4 bytes, so I need one of these boxes. Java picks one for me that's free. Java knows which addresses are used and which ones are free. So it does that bookkeeping and accounting for me and says, okay, Bob can be 216. And then, now that that declaration is done, if I do an assignment, like if I write Bob equals 3, then Java remembers that Bob lives at address 216 and stores that 3 there for me. One of the things that makes computers interesting is the fact that you can store these memory addresses in memory addresses. And so memory addresses, when they're stored in memory, are called pointers. And so a simple example of that is I can take the address of Bob and I can store it in another box in memory. I can call that box some other name like pointer. And so I interpret this number, 216, stored in this box, as being an arrow that points from this box to box number 216. That's how we think about memory addresses stored in memory. Now, you can't do this directly in Java, but you can directly do this in C. There are languages like C that let you manipulate pointers directly. Java is not one of them. But you do want to know about memory addresses so that you can know what Java does let you do. It doesn't let you do pointers, but it lets you do something sort of like pointers. We'll see what references really are soon. Now, part of the difference is that C is trying to give you as much control over your computer as possible. So C allows you to get into individual pieces of memory and manipulate them however you want, store things in your own storage format. Java, on the other hand, is trying to protect you from creating bugs. So Java puts a layer of protection over everything so that you can't just write data into an arbitrary memory address the way you can in C. You can only do things like writing into memory by following the official procedures. You have to have the name of a memory location if you want to write into that memory location. Yes? So you mean if you have a reference variable? In Java, reference variables are more complicated than this, and I'll talk about them later, but we're not quite ready yet. So I'll tell you what a reference is in about 15 minutes, I think. But Java references are definitely more complicated than pointers. For now, though, the main point I'm trying to make here is that your computer's memory is just one big array that has no structure at all except for the structure that your program imposes upon it. And the Java virtual machine is imposing a lot of structure for you that saves you from trying to write into an array index that doesn't exist. Whereas C will allow you to write into an array index that doesn't exist, and thereby overwrite one of your other variables, or even overwrite the stack frame by accident without you knowing. So Java saves you from a lot of thought and planning of where to store things in memory. Yes? So how big does Java usually make the memory arrays? Well, I mean, you can kind of think of your computer as just being one array, the whole thing. However, the operating system and the virtual memory system do have ways of creating the illusion that you have multiple arrays that simplifies writing the Java virtual machine. And that's stuff you'll learn about if you take the operating systems course, and probably you'll learn some of it in 61C. But that's a huge, complicated subject I can't go into right now. Other questions? So that gives us enough information that we can talk about one kind of garbage collection. A mark and sweep garbage collector runs in two separate phases. The first phase is just trying to figure out which objects are live and which objects are garbage, and it does that, as I said before, by running depth-first search from the roots. And so that first phase is called the mark phase, because we're marking the live objects. The second phase is called the sweep phase, and the sweep phase does a pass over every object in memory and finds all the objects that were not marked during the first phase and frees their memory so that they can be reused by new objects. So all the objects that weren't marked during the marked phase are garbage, and the garbage is reclaimed so that it can be used to allocate new objects. So now the question is, how does the sweep phase do a pass over everything in memory? Well, that's where those hidden data structures I told you about come in. The Java virtual machine has an elaborate internal data structure for managing the heap. Now, the simplest version of a heap data structure is just a big linked list. You could imagine a linked list where you go in the order they appear in memory, and you have object, object, free space, object, 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 free space, object, so on, all linked together in one big list. And when you need to allocate a new object, you look through that list for a free space that's big enough to hold the new object. In reality, most heap data structures are more sophisticated than just a list. They have additional functionality that helps you find a chunk of open memory of the right length for the object that you're trying to allocate. But that's a topic outside of 61B, which might be discussed in 61C. But the way to think about it is there's an invisible linked list that links everything, every object, and every bit of free memory. And the Java virtual machine can go through this secret linked list and figure out how to either find memory to allocate you a new object or get rid of an object you've already got and turn it into free memory. As it's going through that list during the sweep phase, it looks at each object's visited tag, and if an object has not been visited, it's garbage, and therefore you can turn it back into free space. So what happens is usually a program is running, and then suddenly it will pause for a brief instant to do garbage collection, and then it will go back to running again. Question in the back there? Does the linked list keep track of itself? Not really, no. The linked list that I'm talking about, like the secret hidden linked list that the Java virtual machine uses, is not made of objects itself. So it's just made of very basic memory scribblings called heap tags. Now, one interesting thing that happens in the heap, you have objects of different sizes. And since not every object is the same size, you wind up in situations where you've allocated a bunch of objects, you've freed some of them, but you haven't freed others, and that leaves you gaps of empty memory between the objects, and those gaps aren't necessarily big enough to accommodate the new objects that you want to allocate. And so that problem is called fragmentation. And the solution to fragmentation is something called compaction, which means we're compacting the heap. So again, you allocate a bunch of objects, you free a bunch of objects, garbage collect them, others you don't garbage collect. You wind up with fragmentation. Which is the tendency of free memory to get broken up into lots of small pieces. And the problem with fragmentation is it might leave you in a situation where you have lots of free memory, and yet you can't allocate a large object because it's all broken up into little pieces. So what that would look like is, if you imagine that this array represents all the memory that the operating system has made available to the Java virtual machine, and maybe you have an object here, and an object here, and an object here, and an object here, And there's lots of bits of free space between those objects. And if you could add up all those bits of free space, you'd have a big chunk of free space where you could allocate a big new object. But that big new object is too big to fit in any of those little spaces there. Fragmentation also can cause other problems, like it can cause the memory caches to be slower. It can cause the virtual memory to page more often. These are things you'll learn about when you take 61C or 152. But a compacting garbage collector can fix this problem. And the idea is that during the sweep phase, you actually take these objects and you pick them up and you move them so that they're all right next to each other. And so after you've done compaction as part of the sweep phase, all your objects are tightly together at the beginning of your memory space. And now if I want to allocate an object that's this big, I've got room to do that without asking the operating system for more memory. Are there any questions about that, compacting? Yeah. Runtime? What do you mean by that? I mean, the short answer is linear time. It runs in linear time. Depth first search runs in linear time. Everything here is essentially linear in the number of objects you have in memory. All right, so now I'm going to come back to telling you what a reference really is in Java. You've been using them all semester. Now find out what they actually are. So I just told you about compaction. And one of the amazing things that we do is we take an object and we pick it up and we move it somewhere else in memory. If you think about it, that's a little weird, because what if you have 100 different references to that object? Don't all those references now point to the wrong thing? The answer is that in Java, references are not pointers. There's something a little more complicated. There's something called, at least there's more than one way to implement them actually, but in the system originally devised by Sun and subsequently taken over by Oracle, references, Java references, are what are called handles, and a handle is a pointer to a pointer. So when an object moves during garbage collection, Java changes the second pointer. The first pointer doesn't change. If you have 100 references to an object, those don't change. And the second pointers are kept in a special table that just contains these special second pointers. So here's the idea. Suppose you have a bunch of references scattered all through your memory that all point to the same object. Well, all those references aren't really pointers to an object. Rather, there's this little box in memory that's just big enough to store one memory address, and all the references point to that. So all these references to an object really point to a little box somewhere in memory that is not the object, but that little box does point to the object. So then, if the garbage collector comes along and says, that object is fragmented, I want to move it somewhere else, I'm going to pick up that object and move it over here. Well, all the Java virtual machine has to do is change that one pointer in the box so that now it points to the new location of that object. And now all of those references are still referencing the same object. You didn't have to go and change the million references that point to that box. You just have to change one pointer in the box, and that lets you move the object. And again, these second pointers here, those are kept in a special table because the second pointers are small. They're just 4 to 8 bytes, depending on whether you have a 32-bit or a 64-bit CPU. And they're all the same size. So you have this special table of second pointers, and if you garbage collect an object, you also garbage collect its second pointer, but you do not have the problem of fragmentation in the table of second pointers because second pointers are all exactly the same size, unlike objects. Objects only have the problem of fragmentation because objects come in different sizes, and you might not be able to fit a big object where there used to be a small object. But in this table of second pointers, they're all the same size. When you stop using one, you can reuse that space for a different second pointer for any object. Any questions about that? Yeah. Of which second pointers are being used? Yeah, there's several tricks you can use for that. I don't actually know the Sun JVM specifically. One way would be to have an array of bits where you just have one bit for each entry in the second pointer array, and those bits are either 0 or 1 for free or allocated. A second way you could do it is you could actually link all the free pointers together in a stack. And that way you don't even have to use an extra bit of memory for each special pointer. Yes? Right. So does this change how we draw our stack and heap diagrams? And the answer is no, because this stuff is all hidden from you by Java, and we want to keep it that way. The only time when you would actually really need to know this is if you yourself are writing a compiler. If you were writing the Java compiler and the JVM, you would need to know this very intimately. But since you don't, it's just a curiosity. Mm-hmm. Next, I want to talk about another kind of garbage collector. It's related to mark and sweep garbage collecting, but it's faster. And it's called copying garbage collection. And again, it's faster than mark and sweep. because there's only one phase instead of two phases. We don't have a separate mark phase and a separate sweep phase. We're kind of combining them into one. But there's a disadvantage. In order to be able to combine them into one, what we're going to do is basically cut our memory in half. So we take our memory and we divide it into two spaces. And those are called the old space and the new space. So the copying garbage collector is going to find the live objects by depth first search, just like the mark and sweep garbage collector does. But it's not just going to mark them. Instead, when it finds a live object that it hasn't found before, meaning when it encounters a live object in the old space, it immediately moves that object into the new space. So there's not going to be a second pass for sweeping and compaction. We're going to do both those things right now. As soon as we find the object that's live, that we haven't already moved to the new space, we move it to the new space. And so that object will be moved to the first available location in the new space, so we get compaction more or less for free. And after all of the objects that are live have been moved to the new space and we're done the depth first search, then we just forget about all the objects in the old space. It's like we just don't have to ever think about the old space again. It's dead, it's a graveyard. You can wipe it out with zeros and start over fresh. Actually, you don't even have to wipe it out with zeros. So there's just no need for a sweep phase of any kind at all. And again, you get compaction automatically, just by moving things from the old space to the first available free space in the new space. Now, next time we run the copying garbage collector again, we're going to swap the spaces. So the space that was the new space last time, now we call it the old space. The space that was the old space last time, now we call it the new space. So after two passes of copying garbage collection, the objects have swapped from one space to the other and then back to the one they started in. And if an object happens to live for a long time, it can swap back and forth between the two spaces many, many times. While your program is actually running, meaning between garbage collections, all of the objects are in one of the two spaces, which means the other space lies empty, it's kind of being wasted. So there is a big disadvantage here, which is you only can use half your memory, but it's definitely fast. But the amount of memory that your program can use is effectively cut in half. Or at least the amount of heap memory. It doesn't affect the stack. Any questions about copy and garbage collection? Yeah. I don't really know when Java chooses to garbage collect, actually. It's pretty variable from JVM to JVM. There are no official rules. It certainly does it when it suspects that there are lots of unused objects and it needs more memory. So the most likely time for it to happen is when you construct a new object, you need new memory, and Java thinks it's more likely to be able to resalvage the old memory rather than having to get more from the operating system. Yeah, question here. I'm not sure about that. There might be a way to disable garbage collection. I haven't looked into it. Java has a billion features. I don't know all of them at all. But most languages with garbage collection do allow you to have some control over it. But again, that may vary from compiler to compiler too. Other questions? Here. So, no, most JVMs have a specific garbage collector built in. And in fact, I'm going to talk next about one version of the JVM, and it's actually got a sophisticated garbage collector that combines these techniques. Was there a question back there? What happens if a new space is too small? Right, so there are several choices. The question is, what happens if in this copying collector the new space is too small for what the next thing you want to allocate, even after you've compacted? One option is sometimes the JVM can request more memory from the operating system, in which case it can expand the sizes of those spaces and then continue running from there. But sometimes you're authentically out of memory, and then the JVM throws an out-of-memory exception, or actually I guess it's an out-of-memory error is what it's called, and your program can't continue. Any other questions? So studies of garbage collection show that most objects die very young. Most objects are created briefly, used for an instant, and then kind of garbage collected very quickly. On the other hand, it also experimentally show that typically if an object lives a long time, it's very likely to continue surviving. Objects that live for a while are probably going to get really old. And so this observation has inspired what are called generational garbage collectors that treat young objects differently from old ones, because the young ones are liable to live wild and die young, and the old ones are liable to hang around in the same place for a long, long time. So it makes sense to treat them differently. And we treat them differently by dividing objects into 2 or more generations. Now, these generations are a little bit like the two spaces or the multiple spaces in a copying garbage collector, but they're not quite the same thing for a number of reasons. One is that different generations can have different sizes. And in fact, their sizes can adapt depending on how many young objects are around and how many old objects are around. So they can actually change size during the program's lifetime and grow and shrink according to the number of objects they actually have to store. And so I'm going to talk specifically about how Sun did the version 1.3 JVM. I'm not sure how much they've changed it since then, but it's a really good case study regardless, so it's a nice way to do things. So the idea is that, first of all, if you imagine this big box as being the heap, then it's divided into an old generation, which is relatively simple. So objects that have been around a long time are up there at the top, and a young generation. Now, in the old generation doesn't change very much, doesn't change very quickly. So we're going to use a mark and sweep garbage collector. But we're going to use it infrequently. The idea is that old objects tend to be set in their ways. They don't change very fast. They don't get new ones generated very fast. They don't tend to die very much. If they've lived a long time, they're probably going to live a lot longer. And so we don't have to do garbage collection of the old generation nearly as often as we have to do garbage collection of the young generation. So we'll do the young generation a lot more often. Since we're not doing garbage collection of the old generation very frequently, we don't need to stress the speed of the garbage collector for the old generation. So we just use a mark and sweep. That way it takes less memory. And if the old generation is really big, if it takes a lot of memory, that's a good thing. We don't want to double up on memory for stuff that's been around a long time, especially if there's a lot of it. The young generation is actually kind of divided into two spaces itself. The bottom half of the young generation is called Eden. Don't know why they named it Eden, but all objects are born here. And most objects will die here. Aww. Because, as I said, most objects are short-lived. Studies show that most objects get created, used like a flash in the pan, and then discarded. Poor objects. But so there's no point in worrying about garbage collecting them much, because most of them aren't going to survive the first garbage collection or two. However, when Eden fills, Eden is just a big, quick and dirty way to create objects until it gets full. And then when it's full, you just immediately promote the live objects up into the upper half of the new generation. And the upper half of the young generation is going to be a copying garbage collector. So I'm drawing two boxes here. I want you to think of those as the two survivor spaces, as they're called, of a copying garbage collector. And this copying garbage collector is expandable. So if there are lots of objects that survive Eden, then you make the copying garbage collector bigger, the survivor spaces get bigger, to make room for those extra objects that survived. So again, when Eden fills, any live object in Eden that hasn't already become garbage gets promoted up into the copying garbage collector. And then it gets copied back and forth between the two survivor spaces many, many times. And we keep track of how many times they get copied back and forth. And then when objects get really, really old, they get tenure. So the idea here, though, is that the generational collector is trying to take advantage of the best features of both the mark and sweep garbage collector and the copying garbage collector. So the young generation is pretty active. Things are being created and dying all the time. So you want speed in the young generation. And so that's why you use the copying garbage collector there, especially since garbage collections are frequent. So you want them to be as fast as possible. In the old generation, you don't have to garbage collect very often because things don't change very often. But you can then you use mark and sweep because it's more compact. It takes less space. There is one. Oh, let me just write the two types of garbage collection. There's what's called minor garbage collections, which happen frequently, but only affect the young generation. Saving lots of time. And there are what are called major collections that don't happen very often, but do depth-first search over all the objects in memory. But this introduces another problem, which is, suppose that there is an object in the young generation that is live only because some object in the old generation references it. The question is, when we do a minor collection, we're not doing depth-first search on the old generation. So how do we know that that young object is live and that we should not collect it? And the answer is, apparently these kinds of references from the old generation to the young generation are relatively rare. So studies show that they're sufficiently rare that, as a general rule, you can just keep a special table in which you store every reference that points from the old generation to the young generation and use those as the roots of your garbage collector. Hmm? Yeah, when you do a sweep of the old generation, you're doing a sweep of everything. Mm-hmm.
And also, roughly, what would this commonly correspond to? So would it be maybe that Eden's young generation might be variables that introduce as arguments of functions, and then you have global variables as older ones?
I'm sorry, I didn't get the first sentence.
What's the approximate time scale, so to speak?
What's the time scale of what?
So you have Eden and you have all the young objects.
Mm-hmm. Yeah, or objects that are returned by a method and then discarded immediately after they're used. Those are the kinds of things in Eden, right? Does that answer your question, or was there more? Okay. Any other questions about this? In the back there. So you're suggesting that a Java program should be able to specify that it expects an object to be short-lived, and so just put it somewhere other than the heap, the stack or something? Might be a good idea. In C, you can actually do that. In C, you can have an object, or a structure really, that lives on the stack and not on the heap. I think with Java, part of the reason why they didn't do that is they just wanted to have a simpler model. One of the original purposes of Java when it was designed was to have a language that you could debug on one Java virtual machine, and then it would run exactly the same way on any Java virtual machine. And so simplicity was part of the model. They wanted to control how programs were executed and keep them as simple as possible, so that the kind of thing you suggested would make a lot of sense in a systems language like C, but did not make sense for Java when it was designed. Mm-hmm. I'm sorry, can you speak louder, please? Do objects in Eden? Objects in Eden, the very first minor garbage collection, an object in Eden is either live and dies immediately, garbage and dies immediately, or it is live, and if it's live, it immediately moves up to the survivor space on the very first garbage collection that it survives. Does that answer your question? You could say that. It's like a copying garbage collector that only goes one way. Nothing ever moves back down into Eden once it's left Eden. Does anything what? Oh, no. I mean, Eden doesn't get compacted itself. Any compacting in Eden is an object that is live in Eden during its first garbage collection moves straight up into the first empty space in this survivor space. So everything in Eden does get compacted, but not in Eden. It gets compacted by being moved up to the survivor space. Eden is pretty much never compact. Hmm? Yeah, different collectors are not usually running simultaneously. I mean, parallel garbage collection is a whole other field of study, but you should just assume that everything's happening sequentially here. Mm-hmm. Yes? How can Eden fill when it's being garbage collected? It's only being garbage collected when it fills. Most of the time, no garbage collection is taking place. It's not a continuous process. It's something that gets triggered when the Java virtual machine decides, oh, I need more memory. Other questions? Back there, yeah. I don't actually know what the ratio is, sorry. The thing I read describing this didn't say. That's everything for... Oh, yeah, another question. Is there a way to mark an object to be garbage collected? The answer is no, because as long as you have a reference to an object, Java absolutely will refuse to garbage collect it. If Java could garbage collect something that still had a reference pointing to it somehow, then that would break Java, and Java's not going to let you break Java. But the way to get an object garbage collected is just to make sure you have no surviving references to it. And that's the only way. That's everything I have to say about garbage collection. My last topic for the semester is I want to talk about augmenting data structures by putting them together or giving them extra abilities. This could be an endless topic. There's a whole world of ways that you can take the basic data structures we've learned in this class and give them additional features, extra superpowers, extra abilities that by mixing them with other data structures. And you have seen some of this already in Project 3. For instance, in Project 3, well, you already knew some graph data structures, but those graph data structures didn't do everything as fast as possible. So what we did in Project 3 was we added hash tables to the usual adjacency list representation of graphs, and we figured out a way to combine them so that all of the operations that you might want to do on a graph do run in the fastest possible asymptotic running time. And so again, we want to model a set E of edges, and we want to be able to do all kinds of things with that asymptotically fast. So what we did is we stored the edges as a hash table, and we also stored them as an adjacency list. And so I want to just I just want you to think of that as a way of augmenting data structures by putting them together so that they have more power together than they had apart. And the power they have in this particular case is that you can query edges in constant time, or even add and remove edges in constant time. And yet you can still query all the neighbors of a vertex in time proportional to the degree of that vertex. So everything you'd want to do, you can do as asymptotically fast as possible. Another example of doing the same thing is suppose I want to have 2, 3, 4 trees with one additional superpower, the ability to find the neighbors of a key that's in the tree really fast. And just to keep this example simple, let's assume that there are no duplicate keys in the tree. We never actually add duplicate keys. And there are ways to do what I'm about to tell you that do allow duplicate keys, but I'm just not going to talk about that because that just complicates the basic idea. And I just want to get the basic idea across. The goal of this data structure is you are given a key K, and you want to determine, first of all, whether that key is in the tree, and what the next larger and next smaller keys are. So, in other words, the two keys that are closest to K, one being larger and one being smaller. And we're going to call those two keys the neighbors of K. And I want to be able to do this query in constant time rather than log n time. But I still want to do all the traditional 2, 3, 4 tree operations like insert and remove in log n time. So, how do I do that? Well, any ideas? Yes. So, sorry, what exactly will the hash table maintain? Okay, so the hash table will store for each key. Sorry, did you mean say the node in the tree or something else? The what? Well, the key and the information you want. So yeah, you're on the right track. The thing you want is to actually store the neighbors of each key in the hash table. So, like the direct approach, just store the thing you want to be able to query. So, as you say, combine the 2, 3, 4 tree with a hash table. And that hash table is going to map each key that's stored in the tree to a record that first tells us that that key is in the table, but also tells us right off the bat what the neighbors are. So, if I may draw this, here's a hash table. If the number 5 is in the tree and the next smaller key is a 4 and the next bigger key is a 9, then let's store a record that's associated with the key 5, and the record actually says the next smaller neighbor is a 4, and the next larger neighbor is a 9. And so if you have this stored in your hash table for every key, then obviously this allows me to do what I want, look up that information in constant time. But now the question that remains is, when I do an insert operation or a remove operation, can I keep this table updated also in log n time? Did you have a question? Okay. Yes?
Is this process then more memory intensive but has a fast running time?
This process is more memory intensive and has a fast running time, just like Project 3. And so the trick to doing this is making sure that insert and remove still run in log n time. Now, insert is actually the harder one of the two. When you do an insert, you do a tree search, as usual, into the 2, 3, 4 tree. To insert the new key, but you can also, in log n time, find the next smaller and larger keys. That takes a little extra searching in the tree, but it's not hard to do, and it can be done in log n time. And then you need to create an entry for that new key that you just inserted in the hash table. But you also need to update the entries for its two neighbors. So when I insert the 5, I need to update the record for 4 so that it knows that its next larger neighbor is a 5 now and not a 9. And I need to update the record for the 9 to let it know that its next smaller neighbor is a 5 now and not a 4. So in other words, I have to update all 3 keys. In the hash table, but I can do that in constant time. Or to be precise, constant expected amortized time. So add it all up, and my insert operation still takes log n time. The constant is a little bigger, but it still takes log n time, and I can do this other operation in constant time. Similarly, you need to update the delete operation, but that's even easier. When you remove 5, you need to remove 5 from both the 2, 3, 4 tree, that takes log n time, and you need to remove it from the hash table, that takes constant time, and you need to update 4's record in the hash table and 9's record in the hash table so that they don't think that 5 is their neighbor anymore, so that they know that 4's neighbor is 9 and 9's neighbor is 4. But you can update the hash table with all that information in constant time. So again, it takes a total of log n time to remove a key from this hybrid data structure. Any questions about that? Yeah. So storing reference to the actual node would not make insert or remove faster because you still actually have to go all the way down the the 2, 3, 4 tree to do the insert and the remove. There's no way around doing the insert and remove algorithms that we taught for 2, 3, 4 trees. So you're going to find the node anyway when you're restructuring the tree. For the find operation, the find operation, if you have a reference to the node in the tree stored in your hash table, that doesn't actually help you find the neighbors any much faster. It might still take an additional log n time to find that item's neighbors in the tree. Oh, storing references to the neighbors. This could actually be references to the neighbors. It doesn't. I'm not necessarily just storing the key here. I could be storing references to the neighbors. Yeah. The thing that a hash table won't do is when I insert a 5, a hash table won't tell me that 4 is the next smaller key and 9 is the next larger key. So there's the ordering part. Hash tables don't do ordering at all. And that's the part you need the 2, 3, 4 tree for. So that's why a hash table alone isn't enough. Yeah.
When you were doing the 2, 3, 4 trees with non-augmentation at all, did it remove insert and find take log n time?
Yes.
What kind of advantage, time-wise advantage, did this give us?
This gives us a time-wise advantage only for the original query that I talked about, which is I want to be able to do this kind of query in constant time. And so I'm imagining that there is some application that wants to do this query very frequently. If there isn't, then there's no reason to do this. The only reason you do this is because you have some application that for some reason needs to do this query a lot. Other questions? All right, I want to go into a more tricky example, but this is not going to be combining two operations. This is just going to be a way to modify splay trees that makes them more powerful. Sometimes it's really useful for a binary search tree to record extra information in each node, such as the size and the height of each subtree of the tree. If you can record this information in your tree, and if you can update this information quickly every time you update the tree, then you can use this information to do some interesting things. I'll give just one example here. So in splay trees, this kind of information is relatively easy to maintain. First of all, let's look at a rotate right operation. So remember that a rotation is where we have a part of the tree, a subtree of your tree, rooted at y that looks like this, and we do a little rotation through y, which brings x up to the root of that subtree and brings y down. and B gets shifted from being one of X's children to being one of Y's children. Having done that, we can now quickly recompute the size of the subtree rooted at Y, because the size of that subtree at Y is the sizes of its two children's subtrees, B and C, added together plus 1. And once you've computed Y's size after the rotation, you can also update X's size in the same way. And I can do a similar thing for the heights. By the way, to make these last two formulae work out for the height of a tree, we're going to use the convention that the height of an empty tree is minus 1. By empty tree, I mean one that has no nodes at all. Not even a root node. But if you use that convention, then these height formula work out for any node in the tree. So what these formula mean is that whenever I do a rotation, I can, in constant time, update the sizes and the heights that I'm storing for those subtrees. Now, I may also be changing the heights of Y's ancestors. Those won't get updated right away, but they will get updated later when I splay X to the root. So what I just said is that when you do this rotation, it doesn't just change the heights of X and Y, it changes the heights of their ancestors as well. Yes, if I wanted to maintain the depth of every node in the tree, that would actually be pretty hard, because this one rotation changes the depth of everything in subtrees A and C, and there's no fast way to update that, at least not directly. So this trick doesn't work for depth. So again, the rotation will also change the heights of X's ancestors, and those don't get updated, at least not right away. But remember, this is a splay tree, and X is going to get splayed up to the root. So we're going to be doing more rotations, and those rotations are going to fix the height fields for all of X's ancestors. Question here? Mm-hmm. To get the depth, what was your suggestion again? Okay. No, because the height of the ancestor might have the value it has because of a different branch of the tree. So that's not going to work out. All right, so I want to just give you an example showing that I can insert a new item into a splay tree and maintain the size field correctly in such a way that once I splay the new node to the top of the tree, I will have fixed all the size fields. So to demonstrate that, here's just a simple example where I'm going to draw numbers here. These numbers are not keys, they are the size field. So again, this is a splay tree, it is a search tree, but these numbers are not keys, which is why these numbers aren't obeying the binary search tree property. I'm not showing you the keys. Just assume that there are keys here and that they're in the correct order. What I am showing you instead of the keys is the size field. And now I want to show you, let's assume that we start with a tree in which all of the nodes correctly know the size of the subtree rooted at that node. And now let's see what happens if we insert a brand new node right here. Okay, so as soon as I insert x, now all of the size fields on the path going down to x are wrong. They're all off by 1. But I'm going to splay x to the root anyway, and as x gets splayed up to the root, all those numbers are going to get fixed. So the rule here is that since x is a right child of a right child, we're going to start with the zig-zig rule, which means we're going to start with a rotation through x's grandparent. And so I'm just going to show you the first zig step before we complete the zig-zig to see what's going to happen when we update those size fields. So when I do that rotation, the 2 moves up, the 4 moves down, except they're not really the right numbers anymore, but they're going to get recomputed. So I've left blanks in the 2 that are going to get recomputed during this rotation. First, I recompute the size here, which is going to be 1 plus 1 plus 1, and that's 3. And then I'm going to recompute the size of this subtree rooted at that node, and that's going to be 3 plus 1 is 5. So now after my first rotation, everyone in the tree rooted at the 5 knows their correct size. And now if I finish the zig-zig maneuver, that brings the x up again. And the x needs to get the correct number, or the correct size field. And it does. When you do this rotation, the size field here and here get updated correctly. And now the new key that we're inserting is now a left child of a right child. So we're going to do the zigzag rule. I'll do both steps at once here. So now that brings the new key up so that it's second from the top of the tree. And then finally, the new key we inserted gets splayed all the way to the top. And now, at this point, finally, all of the keys in the tree have the correct size field for their subtree. Any questions about that? All right, so the next thing is, once we have this information, how can we use it? Well, there's a variety of different kinds of queries, database queries, that you might want to do that you can do very quickly when you have this kind of information, like size information, in your splay tree. And the example I want to talk about is, how do you answer the following query? How many keys are there between X and Y? Let's say between X and Y inclusive. Now, what's interesting is that if there are n keys in the tree, the number of keys between X and Y could be anything from 0 to n. There could be a lot of keys between X and Y. I want to figure out how many there are without actually having to count them all. And it turns out that you don't have to count them all. You can answer this query in log n time. Or, to be precise, log n amortized time, since it's a splay tree. And that's a little bit amazing, because the number of keys in that range might be really big. Maybe half the keys in the tree and over 2 keys are in the range or more. But we can still answer the query in log n time, which is much, much faster than actually having to look at all the keys. Now, to keep it simple, I'm going to assume that there are no duplicate keys in the tree. That doesn't mean this trick can't be done with if you have duplicate keys in the tree, but the trick is a lot easier to understand if there are no duplicate keys. So I'll just show the easy version. So here is our strategy. I'm going to have a variable, call it C, which I'm going to initially set to n, the number of keys in the tree. Then what I want to do is I want to subtract the number of keys less than x, and then I want to subtract the number of keys greater than y. And what's left over is the number of keys between x and y. So again, my trick is going to be to count all the keys that are outside the range, x, y, and then subtract that from n, and that tells me how many keys are inside the range. So now, how do I figure out how many keys are outside that range? Well, I do it like this. First, I run find on x. And after you do this, all of the keys in the left subtree of x are going to be less than x. And that's going to be true even if the key x is not in the splay tree. So for instance, suppose I do find for on a splay tree, And that splay tree doesn't actually contain 4. And instead, after I do the find for, I get something that looks like this. Well, a cool thing about a splay tree is even if 4 is in the tree, 4 will go to the root. But if 4 is not in the tree, one of the keys closest to 4 will go to the root, either the 3 or the 5. Either the biggest key that's less than 4 or the smallest key that's greater than 4 will wind up at the root. So then what I can do is I can count how many keys are in that left subtree. I know that those keys are all less than x, so I just subtract those out. I also look at the root key and I check whether the root key is less than x. It might be less than x, it might be bigger than x, I don't know. But if it's less than x, we subtract 1. There we go. So by the way, this last case is only possible if x is not in the tree. So now we have counted how many keys in the splay tree are less than x, and we've done it in log n time. And now we just do the same thing symmetrically for all the keys that are greater than y. So I do find y. So for instance, in this splay tree, the same splay tree as before, if I do a find 7 now, then I get this tree here. And so once again, I'm going to subtract out the number of keys in the right subtree because all of those keys are bigger than 7. Yes? You find x and then find y? So if you find x and then you find y, it's not always the case that x will be a child of y right after that. X might be a grandchild of y after that. It depends what the last move is that gets you to the root of the tree. But if the last thing you do to get y to the root is a zigzag, then x will be a grandchild of y instead of a child. I mean, you can still do something. There's still an alternative, but it's not going to be simpler than this. So once again, in this example, we're going to subtract out the size now of the root's right subtree, because all those keys are greater than y. And again, we're going to look at the root, which is a 6 in this case, and see if it's bigger than 7. And if it is, we subtract that one out as well. But for this example, it's not. So once you've done that, C is the number that we're looking for, the number of keys in the range from x to y, inclusive. And for this example that we looked at here, essentially we have 7 keys in the tree to start with. Then we subtract these 2 that are in the left subtree. We subtract 1 because this root 3 is less than 4. We subtract these 2 keys in the right subtree after the second find, and that tells us that the number of keys between 4 and 7 is 2 keys. In fact, they're these 2 keys, 5 and 6. So we did get the correct answer. Of course, this is a really small tree, so that doesn't look that impressive. But if you do this with a tree with 1,000,000 items, the fact that you can do it in log n time is impressive. Are there any more questions about that? Question over there? No. All right, well, once again, please don't forget about the network contest Monday night, 7 o'clock, 306 Soda. You're all welcome to enter. We hope we'll have an exciting competition. And Monday for the lecture will be the sorting video. See you then.